Welcome to Day 2 of Microsoft Research Summit. Yesterday, we discussed what we can do together to enable a more resilient and sustainable world, about work happening at the frontiers of large-scale AI, and about efforts to catalyze the next paradigm of scientific discovery. For today's plenary session, I'd like to introduce Johannes Gehrke and his colleagues within research and across Microsoft, who are rethinking how we build and operate the cloud from the atoms up.
Hi, I'm Johannes Gehrke, Technical Fellow and Lab Director of Microsoft Research at Redmond. At Microsoft, we aspire to enable every human organization on the planet to achieve more. What amazes me again over and over is the scale of the resources that we can apply to this mission and how much these capabilities have grown over time. My first computer was a Commodore 64 with 64 kilobytes of RAM. Persistent storage was first a tape recorder and then later an attached floppy disk drive. A typical modem at that time ran at 1200 bits per second. 10 years after Commodore released that computer, in 1992, Microsoft set up its first internal data center. It was very different than today's data center. It had about a dozen mainframes and 650 PCs running in one building in our campus here in Redmond. Today, with Azure, we now have a planetary supercomputer at a scale that would have been hard to fathom back then and even hard to grasp today. We have data centers in more than 60 regions across the world, containing more than 4 million servers connected by over 175,000 miles of fiber, including undersea cables. This is more fiber than you would need to circle the Earth 7 times. And we have over 190 points of presence that give you local access to this network, and you can connect at up to 100 gigabits per second. That is a factor of 10 to the 8 faster than 40 years ago. The workloads we're running on this planetary supercomputer are equally stunning. We've already heard in the previous track on large-scale AI how new workloads on model training and inference are huge. In recent years, the number of parameters in our most advanced large AI models has grown exponentially, well into the hundreds of billions of parameters, and this growth is continuing. The new capabilities that these models make possible are inspiring even more progress, with AI now helping translate languages in real time, transcribe customer service calls, answer customer questions using natural language, and even help developers write new code. And despite all the compute capacity we have at our disposal, our work isn't done by far. As you will learn throughout Research Summit, we're continuing to advance the state of the art with these models, while also making significant investments in improving their efficiency, so they can better meet customer demand for AI. And the cloud does not stop in our data centers. With Azure Arc, we're extending into our customers' data centers. This is a unified control plane that allows you to manage your resources across Azure and on-prem resources. More recently, with Azure for Operators, we enable the telecom industry to bring their compute workloads to a low-latency 5G edge. And individual customers already have an edge cloud because every time you use Teams, you use Outlook, you use M365, you're relying on Microsoft to defend your edge devices and software against attacks. You rely on us to make sure that your devices are up to date. And every time you give us feedback in any of our applications, such as Microsoft Teams, you allow us to learn from this feedback to make the experience better for all of our customers. When I was working in Teams, we had the motto, every call makes the next call better. And we live by this every day to continuously improve our services. As I said earlier, our mission is to empower every person and organization on the planet to achieve more. And sometimes that involves getting off the planet, which is why we're bringing the cloud into space. With Azure Orbital, we have a ground station service that allows you to download data anywhere across the globe. And we continue research on space, for example, through a new geographically distributed ground station design that uses low-cost commodity hardware to offer low-latency, robust downlinks. Well, so this is all impressive, but there's still much more we can do to make this planetary supercomputer more capable, more reliable, easier to manage, and more accessible to every human and organization on the planet. And much of this involves fundamentally rethinking our approach at every level. And that's what this session is about. At Microsoft Research, we are rethinking the physical layer of the cloud through new storage media, including glass and even holography, building on the recent exponential improvement and commoditization in optical technologies. We are rethinking the networking layer, both within the data center and for wide area networks, for example, through fast optical switches, where we're imagining a flat data center-wide network topology, as compared to the hierarchical networking topologies today. At the physical layer, we're asking the question of how you take data and store it reliably for hundreds of years. Beyond the physical layer, we also innovate at the control plane. We have this massive scale of computing, the more than 4 million servers that I talked about before, and there's a huge number of different cloud infrastructure services running, from networking to storage to AI and ML services. This is a really huge system from hardware to software with very demanding goals of availability, reliability, performance, efficiency, security, and sustainability. We at Microsoft Research envision that we can automate the operation of this infrastructure with large-scale AI through ubiquitous cloud intelligence. The vision that we can automate monitoring, fault diagnosis, and mitigation through the combination of AI with minimal human assistance. For our systems that need to be running 24/7 and need to be always available, this is an area where Microsoft Research has already had huge impact, for example, through research on failure prediction and on intelligent resource allocation. And we have an exciting research agenda ahead of us in making it even less and less necessary to have any human intervention. Let's first talk about the work we're doing to advance the future of the cloud using photons. For this, let me turn to my colleague, Anne Rostron, Distinguished Engineer and Deputy Lab Director at Microsoft Research Cambridge.
Hi, I'm Matt Rostron, a Distinguished Engineer here at Microsoft Research in Cambridge in the UK. And I'm here to talk to you about the future cloud infrastructure. And if we look at the cloud today, everything that it is doing is underpinned by the infrastructure, the storage, the networking, and the compute that we deploy. It's hard to imagine at the scale at which Microsoft and other cloud providers deploy hardware. In fact, I remember about a decade ago going to visit one of our data centers in Dublin. And it was an amazing experience. We basically arrived on the site and we just went round basically what was almost like an arena of halls full of hardware. Now, of course, this hardware runs a large number of workloads, and these small workloads all aggregate together to create a very large workload. And it is that large workload that allows us to think about how to run all this cloud infrastructure efficiently. We get economies of scale, which help drive the costs down. But the other thing that's really important for the cloud is that we depend on the evolution of the hardware that we're deploying. Every generation, we get slightly more performance or slightly better performance for the cost, which helps drive down the costs of deploying the cloud. Now, we are critically dependent upon that hardware innovation. And it is really becoming more and more important for people like Azure and the cloud providers to drive hardware innovation. And when I mean that, when I talk about that, I don't just mean innovation at the silicon level, creating new SOCs, creating AI accelerators. I also mean at the device level. Things like the actual storage devices, the networking devices, the optical transceivers that we use. And one of the things that we have to do is effectively use cross-layering all the way down to almost the atom. So we have to rethink how we build this hardware in order to give us two things. We need to be able to keep increasing that unit of performance per dollar. And also, we need to think about how to build out hardware that is more sustainable. At the moment, a lot of the technology we're deploying comes at a high sustainability cost. By thinking about all these things and cross-layering and co-designing across hardware, software that runs on it, we're able to think about things like stranded resources. And they are the enemy of the cloud. Stranded resources are resources that are deployed, but we're not actually able to utilize at maximum rate. And designing these out as much as possible is really important. For example, we're seeing widespread use of disaggregation in hardware. And that's really about taking components which are normally locked down and used for a single task and trying to make them usable across tasks. Now, why is the time right now to really start to think about hardware innovation? Well, of course, we've all heard of Moore's law ending and the impact that that's having. But I can tell you across DRAM, flash, hard disk drives, tape, even the networking, the optical transceivers we're using, they're all getting to the point where it's actually getting harder and harder to enable the next generation to perform better than the current generation. The easiest way to think about all this is to think of a technology S-curve. If you look at this graph here, on the bottom axis you've got time, and on the vertical axis you've got this metric, gigabytes per dollar, or performance of unit per dollar that you're interested in. Now, when a technology is young, you start off in this ferment phase, where you spend a lot of time, you don't actually make much progress. Once you hit sort of a point, the technology begins to take off, and you get this takeoff phase where you get these usual laws, like Moore's law, or like hard disk drives, capacity doubling every 18 months, or flash doubling every 2 years. You get these laws that we're used to. And then as the technology matures, it rolls over into this maturity phase. And the real challenge for us is this holds across networking, compute, and storage. And what normally happens is, and if you look at many of the components that we use today, more and more money is spent on trying to get those small performance increases when you're in this maturity phase. The development spend increases, and you're getting smaller and smaller performance gains. Now, I've been fortunate enough to work on several technologies that are going through that ferment stage. And it's really interesting because when you go through that stage, you begin to learn about the things that you're going to actually really exploit in the takeoff stage. In one of the tracks today, you'll hear a bit about silica. What's interesting about that is about storing data in a three-dimensional space inside glass, the X, Y, and Z, and voxels that store data. Now, when we were creating that technology, you have all of those properties. Do you think about the number of layers in that piece of glass? Do you think about the XY spacing of the data? Or do you think about the bits per voxel? Which do you push on? If you think of flash, you have a very similar thing where you think about the number of layers. You think about the number of bits per cell. And what's really interesting is you begin to learn what works and what doesn't work. You know, it's interesting that when you start with the technology, often moving from 1 bit to 2 bits per cell doubles the capacity that you can store. Yet, when you're at 4 bits, to get that same doubling, you have to go to 8 bits per cell. And of course, to double again, you go from 8 bits to 16 bits. So what happens is you're developing a technology. You learn the things that are going to be the things which are going to make you easily be able to scale the technology, and the things which are harder. And then as you get towards the end, you go back to revisit the things that you perhaps didn't exploit early on in order to try to think how to keep the technology alive. Now, of course, from the incumbent's view, this is all pain at the end. If you take a disruptor's view, you can think of this maturity of a technology as an opportunity for a new technology. Now, a decade ago, if I was speaking to you and I was being asked, what are the storage technologies that are going to be widely used today in the cloud? I'd probably say to you, tape, hard disk drives, flash. Today, I would give you that same answer. I think it's really likely in a decade that answer will have changed. And the reason is because as these technologies roll over, we make space for the new technologies to take over. And the reality is, it doesn't matter how much the incumbents are spending. There's no escape. We have to spend on these new technologies and create them in order to create and allow the path that we're currently on to succeed and carry on. So across storage, networking, and compute, Microsoft is making many bets on these new technologies. We've publicly spoken in the past about both Silica and our DNA storage work. Both of those pieces of work are trying to answer the same basic question, which is how do we store archival data sustainably for hundreds of years? Today, we use tape. It's a technology that lasts for 7, 10 years. You have to keep recycling to use it. It's not scalable, and it's not sustainable. If you look at other things that we're doing, we're looking at optical transceivers. As the data rates increase in our data centers, the distance with which you can use passive copper cables drops. Therefore, you need to be able to have more sustainable, more cost-effective optical transceivers. And we are looking at technologies moving beyond lasers and glass fibers that may be used. What's more, if I go back to that Moore's law, which we all know has rolled over, we're also looking at new abstractions for compute. And later in one of the tracks, you will hear about our new our analog, optical, asynchronous data flow computer, AIM, that's been designed from the ground up as a machine, as a computer, that is able to solve hard optimization problems. All of these innovations are being driven by the fact that we need to sustain the cloud. We need to make sure that we're able to sustain the increase in performance per dollar spent, and we're able to make the cloud more sustainable. So in the future of the cloud track, we will be talking about several more of these in detail. In particular, Silica and AIM will be covered in depth. And with that, I'm going to say thank you.
Thank you, And. I did some early research on a database approach to sensor networks with ad hoc networking, and I'm always impressed by how far you're pushing the envelope at the physical layer, but then also at the data center networking layer, thinking about how networks are completely redesigned now from the ground up and different from the way networks are structured today. Now let's turn to the application and management layers. I'd like to introduce Dongmei Zhang, Distinguished Scientist and Deputy Lab Director of Microsoft Research Asia.
Hello, everyone. I'm Dongmei Zhang, Distinguished Scientist and Deputy Managing Director at Microsoft Research Asia. Today, I'm excited to tell you about cloud intelligence, aka AI Ops, which is helping to shape the future of the cloud. The most significant paradigm shift in the software industry over the past 15 years has been the massive migration to cloud computing. This shift has brought unprecedented opportunities of digital transformation to business, society, and nearly every aspect of human life. Essentially, cloud computing platforms have become a fundamental part of the world's infrastructure. As a result, the quality of cloud platforms, including reliability, performance, efficiency, security, sustainability, and so on, has become critically important. At the same time, the distributed nature, massive scale, and high complexity of cloud platforms present huge challenges to building and operating such systems. From the lowest level devices to storage, networking, compute, and beyond, these challenges demand innovations not only at each layer of the cloud platform, but also at the entire system level. In addition to research and technology development in hardware and architecture design, artificial intelligence and machine learning, AI/ML for short, are highly important for cloud systems. In fact, AI/ML is a new mindset, new methodology, and new dimension of innovation for cloud systems. While providing unprecedented opportunities of digital transformation for many industries and domains, as I mentioned just now, cloud platforms also need to go through digital transformation themselves. AI/ML is the enabling technology to help cloud systems go through its own digital transformation, which will help achieve Jim Gray's ambition of building planetary scale system used by millions of people, but administered only by a part-time person. To infuse AI/ML into cloud systems, we started the research direction Cloud Intelligence about 10 years ago. It is also known as AI Ops nowadays. Cloud Intelligence is to innovate AI/ML technologies to help design, build, and operate complex and large-scale cloud systems effectively and efficiently. Cloud Intelligence has 3 pillars: AI for system, AI for customers, and AI for DevOps. Each pillar has a specific goal. The goal of AI for systems is to make intelligence a built-in capability to achieve high quality, high efficiency, self-control, and self-adaptation with less human intervention. The goal of AI for customers is to leverage AI/ML to create unparalleled user experiences and achieve great user satisfaction using cloud services. The goal of AI for DevOps is to infuse AI/ML into the entire software development lifecycle to achieve high productivity. Cloud Intelligence enables both researchers and practitioners to rethink the human role in cloud systems. Even today, there are still manual operations and rule-based components in many cloud systems, which raises several problems. First, it is difficult for people to monitor the state of the system 24/7 and to solve problems immediately. This often leads to significant delays and user impact. Second, manual and rule-based solutions are rarely optimal. Most of the time, people only see partial data and system state and are often unable to quickly find the optimal solution. Third, maintenance costs are extremely high. Cloud systems evolve and upgrade frequently, which means that manual or rule-based solutions must be maintained constantly to remain consistent with the updated system behavior of the new version. Cloud intelligence strives to make cloud systems more autonomous by automating its DevOps as much as possible, including build, deployment, monitoring, diagnosis, etc. For example, safe deployment is to catch a defective build early in order to prevent it from rolling out to production and resulting in significant customer impact. It can be extremely labor-intensive and time-consuming for engineers because anomalous behaviors have various patterns which may change over time, and not all anomalous behaviors are caused by new build, which may introduce false positives. With transfer learning and active learning techniques, we developed a safe deployment solution that overcomes these challenges. It has been running in production, and it has helped catch defective builds effectively. Cloud intelligence also enables both researchers and practitioners to rethink how actions are taken in cloud systems. A traditional software system takes its input signals, gets the current status of the system, makes a decision, and then executes the decision. This traditional design is reactive, meaning it takes action only based on the current status of the system and its input, which may lead to a couple of missed opportunities. One is that when problems occur, reactive design may miss the opportunity to protect customers from being impacted. Furthermore, it may miss the opportunity to prevent problems from happening at the first place. The other is that reactive design does not effectively learn from the past, and it does not look into the future, which may lead to suboptimal decisions when taking action. Cloud intelligence strives to make cloud systems more proactive by introducing the concept of proactive design. In the design of a proactive system, a machine learning-based prediction component is added to the traditional system. The prediction system takes the input signals, does the necessary processing, and outputs the future status of the system. For example, what the capacity status of cluster A looks like next week, whether a disk will fail in a few days, or how many virtual machines of a particular type will be needed in the next hour. The future status makes it possible for the system to take proactive actions to avoid negative impact on the system. For example, the services on an unhealthy computing node can be live migrated to a healthy one to reduce virtual machine downtime. Another example is to pre-provision a certain number of virtual machines of a particular type for the next hour to reduce the latency of virtual machine provisioning. In addition, what decision to make can also be learned over time using AI/ML techniques. As an example of proactive design, we built a system that takes proactive mitigation actions before potential hardware failures to reduce service interruption and minimize customer impact. This system performs prediction on hardware failures, and it uses a bandit algorithm in deciding which mitigation action to take. Cloud stack ranges from the lowest layer of devices to storage, network, compute, containers, and myriad application services. In addition to empowering the transformation of cloud platforms, cloud intelligence can also help design, build, and operate the layers of services built on top of cloud platforms. The goal is to scale out cloud intelligence technologies across the entire cloud stack to benefit the cloud platform providers as well as their customers. Cloud intelligence has become an emerging technology trend in the cloud industry and an interdisciplinary research direction across system, software engineering, and AI/ML communities. With years of research on cloud intelligence, Microsoft Research has built up rich technology assets in detection, diagnosis, prediction, and optimization. In addition, through close collaboration with Azure and M365, we have deployed some of our technologies in production, which has created significant impact, helping improve the reliability, performance, and efficiency of Azure and M365, as well as the productivity of developers working on these products. Moving forward, we believe that as a new dimension of innovation, cloud intelligence will play an increasingly important role to make cloud systems more autonomous and more proactive across the entire cloud stack. It will help us make the future of cloud a reality.
How are you doing, Mark?
Good, thanks, Johannes. Thanks for having me.
It's great that you're here. So in our plenary session, we've discussed the importance of the cloud and, of course, how the cloud is changing and how the systems infrastructure as well as the operations of the cloud are changing. Can you tell us a little bit about what are the workloads that are driving this and what do you see from our largest customers in Azure?
Sure. Well, certainly the workloads have changed a lot since Azure started back when I joined in 2010. There was the shape of workloads from then to now. First of all, they've gotten bigger. Lots more migration. The rise of cloud native computing has put a lot of requirements into Azure to both innovate and support what customers are looking for. But two classes of workloads, I think, really represent big changes in infrastructure and the way that we run at massive scale. And one of them is AI, which you've talked about. So the rise of large-scale AI models as foundational models. Satya calls them their platforms. And he calls them platforms because these serve as foundational models that you derive or fine-tune other models on top of. One of the most famous examples of such a large model is GPT-3, which was trained on Azure. It was trained on 285,000 CPUs and 10,000 GPUs in Azure.
Scale is amazing.
Yeah, it's just massive scale.
Massive.
And as an example of how that's served as a platform, it can generate language, of course, itself, but a fine-tuned model on top of that is called Codex. And we've taken and productized Codex with OpenAI into GitHub Copilot, which is the pairwise programmer that really represents the future of usage of these kinds of models to assist people in things they do, even very complex things we didn't imagine that computers would be able to help us do, like help us program.
It's really amazing to see these new use cases as well as what's happening now with our customers. And as we're now able to implement things at scale like optics for the cloud or data-driven operations and management through AI ops and cloud intelligence, what do you see as the new workloads and use cases that are rising, and where do you see sort of our customers pushing the edge in some sense of capabilities of Azure?
Yeah, well, this, I think, question nicely sets me up to talk about the great collaboration Azure has with Microsoft Research. And I know that some of these topics are being discussed with their own sessions here. But Project Silica is a great example of a big bet that we took together on the promise of using glass for storage. And this is going after the rise of data, the number of zettabytes, I don't remember hundreds of zettabytes of data that are being generated every day or every year. And traditionally, we've had to just throw a lot away, even if we thought it might be valuable at some point in the future. Or we store it, and it's very expensive to store. And in certain sectors, like the media industry, which has long-term archival storage for what they consider their IP, their core IP, 100 years, right? If you take a look at the promise of Silica for bringing down costs, but also, just as importantly, being more sustainable than traditional technologies. With those kinds of tape or SSD technologies, you've got to rewrite them periodically. And this costs a lot of energy. You're still prone to data loss. They're fragile technologies, believe it or not, compared to glass. Glass can tolerate all sorts of kinds of disturbances and still preserve its data. So Project Silica really, I think, represents the future of archival storage at scale, and that was a great collaboration between Microsoft Research and Azure. You mentioned optics for the data center, and that's another place where we're seeing the end of copper as being sufficient to carry the bandwidths over the distances we need inside the data center. So we've traditionally used optics between data centers. We're bringing optics into the data center, optics between servers and optics in the servers themselves, and that's also collaboration with Microsoft Research on co-packaged optics for those scenarios, and promise major cost savings, major simplification of the data center infrastructure. Those are some examples. And what's driving that, of course, is the kinds of large-scale workloads we saw earlier, and just the desire to be more efficient in data center floor space, data center cost to connect our computers together, the rise of the fact that servers are getting bigger. Even general-purpose compute servers now have up into the hundreds of cores of where they used to, when we started in Azure, had 32 cores. That was considered a big server. So all of this is pushing all of these workloads, and the evolution of infrastructure is pushing the need for breakthroughs to support that kind of scale and efficiency that we're looking for. And then you mentioned AI Ops. That is like foundational to Azure. We couldn't operate at the scale of 65 regions with hundreds of data centers without AI Ops helping us. And that AI Ops used to both detect problems as they're occurring, not just detect problems, but help us diagnose problems and help us mitigate problems. And a great example of that is Resource Central, which is part of planning and making the data center efficient. Strong collaboration between Microsoft Research and Azure for optimizing the way that we leverage compute, and also using predictive capabilities that are in these models that are trained off of what's happening to help, for example, keep the availability of our Spot instances, have them survive longer, which is great for customers, or to predict a failure of a server and move it out of the way, move the workloads off that proactively so that the failure doesn't disturb a workload and the workload survive it. So great examples of that. And again, what is driving that is the scale that we're getting to, the desire for customers for higher and higher availability. You know, they're paying, and we don't want them to pay for cycles that they can't use, right? Effective cycles. We want to maximize the efficiency of our infrastructure for them and for us.
And it's super interesting, especially since, as you said, the data center is changing itself, right? We started to do mainly to think about disk and CPUs. Now with GPUs, I mean, you mentioned, you know, the training of GPT-3, right? With more than 100,000 CPUs, you know, 10,000 GPUs. I mean, that evolution, where do you see that going?
Well, that one, I think custom, so you're seeing silicon go from general GPUs, which were general purpose for gaming and for high performance computing, now being focused on large scale models, and accelerators just for AI models and their requirements. But I think, again, looking forward, like what is the next step beyond that? Well, quantum computing to solve certain kinds of problems. And then MSR is working on some kind of really cool technologies in the space of optical computing for having optical optimization, which also promises 3x, 4x kinds of improvements in efficiency and performance over GPUs used to accomplish the same task, and saving a tremendous amount of energy at the same time. So, and that is, again, kind of cutting edge. We have to see where it goes, and it's going to be a path to commercialize it. But the promise to optimize problems with hundreds of variables or thousands of variables within seconds with optics would be a huge breakthrough.
I mean, in general, you know, these optimization problems are just also so hard, right? It's not only just a simple bin packing problem. If somebody comes in, I want a small instance here, and they should be all in this region over here because of compliance.
That's right.
And then, you know, others because they're really co-located on the network as well.
That's
so
right.
Just...
The number of placement rules in the placement engine, and this is, I think, a lot of these rules are hand-tuned rules that are going to become more AI-driven rules. Yep. But there's roughly 25 to 50 different rules on, and that's the generic rules, not even placement constraints that customers might bring, but just in terms of should this VM go on this server or that server.
Yeah, I know that there's a lot of work at MSR as well to help with the resource center with the all optimization of placement. That's right. It's really exciting. Another area I know that you're very passionate about is security and in general, confidential computing.
That's right.
Can you tell us a little bit more how MSR and Azure are working
Yeah.
together there?
Well, so that's another great example of customer workloads pushing us and us looking to how we can help customers as well in terms of security. We've always had, we've had the rise of encryption at rest. And that's something that you saw at cloud providers. When I started in Azure, there was no encryption at rest. Now there's 2 layers of encryption at rest with the service and customer keys.
So can I think of this like as BitLocker on stereo?
Well, that's right. Well, then there's encryption on the wire. Now we've got encryption in use with confidential computing, where you've got enclaves where code and data are protected from outside tampering and visibility. And the MSR was exploring that area back in the early 2010s, and that's when I caught wind of it and started this deep collaboration with MSR. We actually together coined the term confidential computing, and now that is a widely accepted industry term. In fact, there's a confidential computing consortium, and there's so much work to continue to do there, both in terms of real kind of architecture engineering, but in terms of the science of the cryptography and promises you can make around it. And this is where MSR's expertise is critical in helping define that. And also having the bandwidth to go and explore these kind of future directions where by the time we're caught up, for example, confidential containers, which we announced at Build, MSR was there exploring how should these things look to provide the confidentiality promises we need. What's the best way to engineer those? And then we take it and productize it in an engineering team.
Yeah, that's what I'm always so amazed by here at Microsoft, how well we work together across product and research. I remember because confidential computing in my area in database systems at the beginning was like Merkle trees.
That's right.
Which is just very simple, certify that you actually take the right path and get the right data.
Yeah.
And now we're talking about confidential containers.
Yeah,
So
well, Merkle
really
trees
great.
haven't gone away either, because
Right.
we've got confidential ledger, which is another collaboration with Microsoft Research, which is a blockchain-based, tamper-resistant confidential ledger as well.
Yeah, think of this as like a confidential, like a certified SQL log, right?
That's right.
Basically
That's right. Yeah.
is tamper-proof.
Yep.
Well, super interesting, Mark. Can you tell us a little bit more about how actually MSR has influenced your team, so the decisions that you've made in Azure over the years?
Yeah, well, in a variety of different ways. One of them that I have instituted with MSR is how can we get Azure and MSR to be better coordinated? I mean, I think one of the things that we both saw are because of the way MSR is very grounds up and researchers kind of explore on their own, which is one of the great value propositions of having MSR for that kind of freedom and that creativity.
Yeah, I always felt, even when I was in the product groups before, that MSR has the freedom to really look ahead. But then bringing the context in which the product group is working and bringing some of the thinking also back into MSR is usually some of the best ways of sort of coordinating between product and or even applied science in the product groups, and then MSR as well. And I think you've done this so well in Azure. I mean, even on the data side, right? There's a lot of collaboration.
Oh yeah,
across.
I mean, it's everywhere. Networking, data, storage. But we've already talked about storage, compute with confidential computing, Resource Central, which is compute relevant in AI ops in general. Yeah, there's just been so many collaborations.
Super interesting. Maybe as a very last question that I think the audience is probably also interested in, what do you see as some of the biggest challenges right now that you think, if somebody wants to sort of look 5 years ahead?
Yeah.
What do you think would be interesting problems to work on?
Well, I think that we're pushing the limits of the current technologies, like we've already discussed, for large-scale systems, and looking for the breakthroughs that will take us to order of magnitude improvement in efficiency. In efficiency of energy, I mean, that's for sustainability. Efficiency of the workloads themselves. And
talk about large model training.
That's right, large model training. I mean, it'd be great if we could train those large models in a fraction of the energy that it takes to train them today. In a fraction of the floor space, data centers, in a fraction of the data center area that it takes to train them today, because these things are multiple data centers of capacity. And then I think what that's going to lead to is a complete change of the inside of a data center as well. Today we've got the concept of servers and racks. Well, liquid computing, two-phase liquid immersion is coming, and we've already got that in production. That is going to change the shape of how servers are laid down in the data centers. We're going to see the same thing with networking, and we're going to see the co-evolution, I think, of software plus hardware. So software topology is driving what the hardware needs. Example of AI and large-scale analytics. What does that need to be more efficient from the hardware itself? Where you're designing systems, not discrete parts, and putting them together like we effectively have been.
So you're saying, have some, if I'm a researcher, focus sort of on hardware, software co-design, and
right.
look at where the hardware is pushing it, but then also design the software layer for it.
That's right. I think that's the place that's really, it's a very tough one. I mean, people have been talking about that forever since even in the CPU space. What does the CPU need to do for the software?
Right.
Now we're at what does the data center infrastructure need to do for the data center scale software infrastructure?
Right. Do you see the data center by itself also changing, that it becomes, I mean, I see all of these different, NPUs, GPUs, et cetera, XPUs, whatever, coming along. Do you see the data center itself also changing, becoming much more heterogeneous than it is
absolutely.
right now?
You hit the key part of that, which is the rise of specialized accelerators.
Yep.
And we've seen this rise of accelerators. We touched on that in the area of AI.
Yep.
But I think the rise of AI accelerators in other areas, once you get to a certain scale, it makes sense to go into silicon. Yep. And one of the tools that we've got too, that we're still figuring out how we fit it in to this big picture, is FPGAs, which is the midway point between software and hardware, where you get a lot more agility, and you don't have to get to the same kinds of scales you need to justify going into an ASIC that's custom designed. I think that holds a lot of promise too. And so that's another place, like, how can we leverage FPGAs in a more general, ideally developer accessible way, because today they're not very developer accessible, to make it so that it becomes a general purpose hardware accelerator rather than something that is only for specialized cases that need that kind of agility.
Yeah, and coming back to the research community, right? I think hardware is really hard for the research community because it requires huge capital investments. But one thing I've seen, especially in all of these accelerators, you can have the best accelerator unless you have the right software stack.
That's right.
It's just another brick in the data center.
That's exactly right.
And so, what would your advice be for, software people? What are the classic accelerators you're seeing? You talked about FPGAs. Is there anything else that you see, and how do you see that evolving?
Well, the other types of accelerators, so there's AI accelerators. The reason that I mentioned FPGAs, and of course there's data center infrastructure acceleration, like networks and storage acceleration, which there's already been a lot of progress inside of Azure with contributions from Microsoft Research in those directions as well. Those are ones that, that for that particular functionality are pretty fixed in terms of the surface area. But in terms of large, like take databases for example, we've been looking at, with MSR, what parts of a database can we accelerate in silicon? And that might mean FPGAs initially, if the workload or that pattern of workload becomes large enough scale, then justifies the 3-year investment in building an ASIC for it. But looking for those spots, and in fact, they kind of go hand in hand. How can we program, and FPGAs allow us to experiment too with the software and hardware. So that's a tool for researchers to look at. Of course, with ASICs, you get different performance characteristics, but you can get a rough idea of how you can accelerate using FPGAs today.
Well, super interesting and really inspiring to hear from you. Thanks a lot, Mark.
Thanks, Johannes. Thanks for having me.
It's exciting to see how all the work we're doing in research is helping to meet the growing demands of today's cloud workloads, as well as building the foundations for the cloud of the future. It's also inspiring to hear about all the ways our customers are putting Azure to good use. It's stories like these that connect what we do in research with our mission as a company. We want to continue innovating across the whole cloud stack so that our customers and partners can put our planetary supercomputer to work and do more useful and constructive things for society. If you want to learn more about the innovations we discussed here, our researchers and their collaborators, they will all be sharing much more about their work in the Future of the Cloud track later today. Thank you for watching, and I hope you enjoy the rest of Microsoft Research Summit 2022.